Nice to see a big turnout today. So I'm going to be giving a little bit of an introduction to performance tuning and optimization. This is really the developer topic, but I'll try to keep things pretty high level. I'm happy to take questions as we go along, but it's a little hard for me to monitor the chat. So at the same time, so Cindy, if you want to interrupt me, but when you think it's a good time, feel free to chime in and I'll try to answer those questions. And of course, happy to take questions at the end. So presentation mode. Okay, everybody should be seeing that now. Cindy, does it look good?
Yes, it does.
Okay, again, thank you. Welcome. Good morning, good afternoon, depending on your time zone. My name is Bob Sinkovits. I am the Director of Education and Training here at the San Diego Supercomputer Center. But when I'm not doing training like I am now, kind of my passion and hobby is performance tuning and single processor optimization. So this is a very, very abbreviated version of a half-day session that I hold at the SDSC Summer Institute, which in turn was an abbreviated version of full-day sessions that I've done in performance optimization and tuning. So if you're interested in the Summer Institute content, we have a link to it here. It has also been pasted into the chat. And if you want to see a full version of the presentation that I do at the Summer Institute, you can click on this link here, the second URL. But I think today we're just going to go through some of what I consider the important highlights of the longer presentation. So, just going to start off talking a little bit about, why we want to write efficient scalar or serial code. We're a supercomputer center. A lot of what we do is parallel computing, but under the hood, every efficient parallel program is based on efficient scalar implementation or the underlying algorithms. So, just a few, practical reasons why we're trying to write efficient code. So first of all, optimizing your code is going to reduce your time to solution. And what we really like to see, especially if there are times when we get a big speed up, is that a challenging problem now becomes doable and routine calculations can be done more quickly. So as many of you are domain scientists, and what this means is that you'll be able to do more science in the same amount of time. You can shorten the cycle between job submission and results. Next, computer time, especially in high-end resources, is limited. So we're not talking about an application that you can, that takes a few seconds to run, where turnaround time is not really important, but we're using lots and lots of CPU or potentially GPU time. So, and I forgot to update this. If you're running on now access allocated resources such as Expanse, you'll need to compete with other users. And if you're running in the cloud, you're going to need to pay. So either way, you want to try to minimize the amount of time a particular calculation takes. And then finally, computing uses a lot of energy. And this is probably a little bit out of date, given that computing is really ramping up. And some other areas of energy usage, say like lighting, now that we've gone mostly to LEDs, has been going down. So I'm going to say that this 5% of US energy consumption is really a lowball estimate. So I already alluded to this, and that is, won't going parallel save me? And there's a few things to keep in mind here. So first of all, most parallel applications have limited scalability. I recognize a few of the names on the call. I know that some of you do highly scalable computing, but a lot of applications really don't scale that far. If you have an account on Access, and if you look at what's in the queue using the SQ command, you're going to see that there are lots and lots of applications that just run within a single node, or that even use just a portion of a node, running in a shared partition. So a lot of applications, you're only going to be able to scale so far. And then also, even if your application had perfect linear scalability, there's always going to be something more challenging that you want to do. We want to go to higher resolutions, finer grids, shorter time steps. We want to simulate larger systems, say with more atoms, molecules, particles. We want to add in more accurate physics. We want to do longer simulations, or we might want to do more replicates, bigger ensembles, better statistics. So there's always going to be reasons that we want our code to be efficient. And of course, availability of resources and energy usage are still important considerations. So I've been trying to find a more recent report that this is a little bit out of date. So you could take these numbers and just scale them up. But in terms of energy usage, in 2013, US data centers consumed an estimated 91 billion kilowatt hours. So this is an enormous amount of energy. This was projected to increase to 140 billion kilowatt hours by 2020. So computing has a big environmental impact, and when we do our calculations, we'd like to minimize the energy footprint. Okay, so a few guidelines for optimizing your software is, first, make sure that you don't break your code. I know this sounds very obvious, but I've seen this done already. I've done it myself, where you make an algorithmic change, you implement a clever optimization, and the code runs a lot faster, but now you're getting the wrong results. So we want to make sure that we're not getting the wrong results quickly. Second of all, before you dive in, profile your code so that you know where to focus your effort. So I was just in another meeting before this webinar with some developers of molecular dynamics software, and their code bases are hundreds of thousands of lines. So if you were trying to optimize or tune that code, you couldn't just jump in, start reading from top to bottom. So you really need to do profiling. You don't want to obfuscate your code unless you have a really, really compelling reason. And by obfuscate, I mean writing in such a way that the operations that you're doing are no longer obvious. It would be hard for somebody else to interpret. Except maybe for, you might want to do this in like the key kernel and very, very heavily used applications. But if you do, make sure that you document that, document it well. One of the easiest things you can do to write fast software is to use the optimized libraries that exist whenever possible. Unless you, say, develop linear algebra solvers or eigenvalue solvers professionally, that is your career, that's what you do, you probably want to use a library that somebody else wrote. I'm going to say this is probably the easiest thing that you could do to get fast code. And then also, you need to understand the capabilities and limitations of your compiler. And I'm going to give a nice example of that a little bit later in this talk. And then finally, before we get into some of the details, how much effort should you put into optimizing your code? The amount of time and effort that you spend is really going to depend on a number of factors. First of all, is the code heavily or widely used? If it's a community code where it counts for millions, tens of millions, maybe hundreds of millions of core hours or GPU hours per year, make sure that you could do everything that you can to improve the performance. In the session that I was in earlier, it was a lot of discussion, again, for some very, very heavily used codes of how they could squeeze out 10% more performance, or another way to avoid taking performance hits as they move from one architecture to another. Does the code consume a significant amount of computer time? Is time to solution important? So does it really change your research if you can get the research results more quickly? Is it going to help you solve new problems that you couldn't solve before? So, for example, it's just too time consuming to do the research you really want to do. after you've been working on optimizing your code, have you reached the point where most of the computing occurs in routines outside of your control, say in a linear algebra or eigenvalue solver? If so, you're pretty much done. And then finally, you need to balance, especially if you're a domain scientist, is how much effort should you put into your research versus optimizing the code? So over the years, since I'm employed here at the San Diego Supercomputer Center and on some of my projects, I was actually paid to do performance tuning and optimization. I could dive in a little bit deeper. If you're a graduate student and you want to finish up, you want to publish your results, you want to move on to a postdoc or a real job, you'll probably want to spend a little bit more time on the research. So again, optimize your code if you think it's going to have an impact on your productivity, or if the code is very widely used. All right, so I mentioned profiling. There are a lot of great tools out there. There's Intel vTune, there's AMD's gprof. On GPUs, there's a tool called Insight. These are all fantastic, and if you really get into performance tuning and optimization, I do suggest that you look at these. But a great place to start with very, very, very little overhead is a tool called gprof. Now, this amazes me. gprof goes all the way back to 1982. So in technology terms, this is ancient. This is a really, really old tool. But I'm going to say, when you're profiling your code, where you're trying to figure out where to focus your effort, this is a great place to begin. So first of all, there's universal support by all major C, C++, and Fortran compilers. To date, I have never encountered a C or a Fortran compiler that does not support gprof. It's easy to use. All you have to do is compile with the -pg flag, run your code. It's going to produce a gmon.out file, and then you just run gprof a.out gmon.out. And it introduces virtually no overhead. Now, every once in a while, if you have a code where you're making a lot of calls to functions or subroutines that are not very time consuming, it can skew things a little bit. It could add a little bit of overhead, but for the most part, it's pretty minimal. Now, note that gprof is not what we call a tracing tool. So it's not going to identify bottlenecks in parallel codes. Still, it's a great choice for understanding the behavior of the underlying serial code. And you can use gprof with a code that's been parallelized using MPI. You're just going to get a separate gmon.out file for each process. I'm just going to go through a few more slides on gprof, and then I'll see if we have any questions. So the output from gprof is really, really easy to understand. There are two sections. The top part is what we call the flat profile. And this is just a listing from top to bottom of functions and subroutines ordered by their relative usage. In a lot of your applications, you're going to find that it's a small number of routines that account for the majority of the runtime. So this is a great way to identify those hot spots in your code. What I'm going to be showing over the next couple of slides is a real-life example from an area called flow cytometry. Now, I've also worked on codes where when I ran gprof, I looked at this flat profile, and it was just a single function that accounted for more than 98% of the runtime. And it was a very manageable function. It was 100 to a few hundred lines of code. So that's really an ideal situation. On the other extreme, there was a code that I once profiled where no single routine used more than about 1.5 to 2% of the time. And that was kind of a nightmare to optimize because you needed to focus in so many different places. So getting back to this example, again, from an area called flow cytometry, I ran this on the application, and I found right off the top that there were a few routines, in fact, three routines that accounted for the majority of the usage. There was something called get number pack data. There was main, the main function, and then finally quick sort double. So you don't have to worry about what these do, but for now we're just going to focus on these top three. Let me just check the chat real quick.
Bob, we do have a question.
Yes.
Do you know of funding requirements that incentivize optimizing software code? Or in what scenario have you seen supervisors support this kind of work?
Oh, okay. That's a great question. As far as I've never seen, for example, an NSF solicitation that required that you optimize your code. And in in science or oriented proposals, it's probably not going to be a big factor. But you could put that into your proposal as one component if the optimization of the code is really going to have a big impact on the science. Now, scenarios where you've seen supervisors support this kind of work, yes, I have seen this. So, in one of my roles here at the Supercomputer Center, I was actually funded off of the few generations ago, the Gordon supercomputer. I was actually funded to work with users and to tune their applications. We also had a big component of the Exceed project, which ended last year, called Extended Collaborative Support Services, where we actually had a significant amount of funding to work with users for porting, optimization, tuning, parallelization. So great question. And from Kyle, will Access CI Match plus Premier offer funding? That's complicated. I would defer to the Access people about that. There's kind of a more complex model where they don't have direct funding from the NSF award to do this kind of work, but they are working on some mechanisms where they could pair up researchers who have funding to improve their code with technologists and computational scientists who have that expertise. So we could follow up offline if you want more details on that. Okay, and finally, Igor, yes, yep, great point, Igor. And I know that you've done a lot of optimization on some highly scalable codes. I agree. If you can speed up the code by 10x or more, it is a game changer. Yeah, I'm surprised if a supervisor would say no. But on the other hand, supervisor may only be willing to commit a certain amount of time. Again, it depends on your role. If you are a professional software developer on that project, you'll probably have a little more leeway, as opposed to if you're a graduate student working on a thesis. But yes, you're right. It's hard to tell ahead of time if you're going to be able to get that kind of speed up. All right, with that, so I'm going to move on. Getting back to gprof. So there's also the gprof call graph. And this gives you additional levels of detail, such as the exclusive time spent in a function and the time spent in all of the children, the functions that are called, and statistics on calls from the parents. So here we're going to start at the top. We have function main. So main itself plus all of the routines that it calls account for 97% of the time. You'll notice this isn't quite 100%. There will be some rounding errors in gprof, but you could see that it calls get number pack data is hump and so on, and get number pack data you'll see accounts for 574 seconds of the time, whereas main, what we call the exclusive time spent in main, not the function that calls, was about 112 seconds. We go down to get number pack data, we see that it's called by main. We go down to isHump, we see that it's called by main and that it calls the three other functions. So I don't find that I have to go to the call graph quite as often, but if you're doing what we call inter-procedural optimization, sometimes this is helpful. So value of reprofiling your code. Be sure to reprofile your code after you've done a round of optimization, since new hotspots may emerge. So when I started working on this code, I started working on get number pack data, and I found that I was able to speed it up so much that after I was done, it now only accounted for 26% of the time. But now function main accounts for 41%. So it's not that main got any slower. It's just that get number pack data got so much faster that main now proportionally accounts for a larger amount of time. So definitely you want to profile. If you're going to optimize your code, you want to go back and reprofile. And then finally, it's been 40 years since gprof. Is there anything new? So I mentioned the AMD uprof tool, which we have installed on Expanse, gives you a lot of low-level information on things like cache misses, branch mispredictions, and so on. But this is going to be covered in another session. And with that, I'm going to see there's a couple more questions in the chat. Oh, great question, Joe. Muprof or uprof? It's actually both. If you do a Google search, you can search on both uprof and muprof. They'll both work, except you might get some different materials. And AMD actually uses both interchangeably in their materials. And I see a question here from Juliet. Can gprof be used to help identify parts of the code that use more memory? No, gprof, all it does is add some instrumentation to your code and keeps track roughly of how much time you're spending in that code. All right, so getting into, I think one of the most important topics in performance tuning and optimization is starting with a distinction between what we call compute-bound versus memory-bound codes. So there's a lot of attention focused on how fast is your CPU. You know, what is the clock speed? And that's important for some applications, but for lots of HPC applications, they're going to be memory-bound. And what this means is that the rate at which data can be delivered to the CPU is the limiting factor. And we're going to be trying to apply cache level optimization so that the CPU is not starved for data. Now, we also have what we call compute-bound codes, where the performance of the processor is the limiting factor. So if you've written your code really well to take advantage of data locality, which we'll be talking about shortly, there you can actually get better performance by running on a CPU with a faster clock speed. So in this case, data can be delivered fast enough, but the processor can't keep up. So here, our goal is going to be to reduce the amount of computation done on a given piece of data. Now, in a real application, though, we're often going to find a combination of compute and memory-bound kernels. So in the chat, so a question here from Sugnik. As a computational researcher who assists domain-specific users, what are the main functionalities one should invest time in uprof? Oh, I think the roofline model is probably to me the most important thing that you now have in uprof. The other thing that I use it for is for analyzing cache behavior to see if we have lots of cache misses. All right, so in order to speed up the performance of memory-bound kernels or applications, we need to understand the computer memory hierarchy. So I think a lot of you may have seen figures like this at some time. So it's usually shown as a pyramid, where at the very top we have the registers. This is where we store data, pieces of data that are available immediately for use by the CPU. So if something is in register, it's available on the next clock cycle. We then have L1 cache, which is on the order of tens of kilobytes, which is on chip. So this is done in silicon. You could think of this as being a place very, very close to the CPU for storing data. We then have an L2 cache, which is on the order of hundreds of kilobytes, and an L3 cache, which is tens of megabytes. And some processors, it's actually getting up to around a gigabyte. But that's going to be shared across multiple cores. And then finally, further down on the hierarchy, we have DRAM and disk. And I'm just going to show some numbers from that are relevant to expanse. So these are, I think, a little approximate, but if data is an L1 cache, it's available in 4 cycles. If it's an L2 cache, 12 cycles, L3 cache, 34 cycles, and if it's in DRAM, 270 cycles. So the further we go down in the memory hierarchy, the more latency we're going to have to work on that piece of data. Now, if you look at the absolute times, you go to DRAM, 120 nanoseconds doesn't sound like a long time, but relative to the clock speed, that's very, very far away. So what we're going to try to do is manage our data in such a way that we can take better advantage of cache. And I'll explain that next slide or two. So again, for memory-bound codes, we're really, really concerned about exploiting the memory hierarchy. And to make best use of cache, we're going to keep 2 concepts in mind. And these are temporal locality and spatial locality. So just going back to our figure again, when we need data that's in DRAM, it actually gets loaded into L3 cache, into L2, and into L1. So it always has to move into the cache first. So temporal locality, the idea is that data that was recently accessed is likely to be used again in the near future. So to take advantage of temporal locality, once data is loaded into cache, it's generally going to remain there until it has to be purged to make room for new data. Now, why would it have to be purged? We go back again and look at the sizes of the caches and DRAM. Let's say we're working on a large problem, data structures that are gigabytes or tens of gigabytes or hundreds of gigabytes. You can see that is much, much larger than cache. Only a small fraction of that data can fit into cache at any one time. So with temporal locality, again, once we've done all the hard work of getting data loaded into cache, we'd like to use it before it gets pushed out to make room for something else. If you're a computer scientist, you've probably taken a course in computer architecture where they go into very, very deep detail of cache management strategies, but generally there'll be some variation of what they call the least recently used algorithm. So pretty much the data that's stalest, that hasn't been used in the longest time, is going to be pushed out. Now, the idea behind spatial locality is that if a piece of data is accessed, it's likely that neighboring data elements in memory will also be needed. So to take advantage of spatial locality, cache is organized into lines. I say here typically 64 bytes. I should say at least for standard hardware, I've never seen anything other than 64 bytes, and an entire line is loaded at once. So if I load an element from memory, I don't just get that element. I'll get an entire line of 64 bytes containing that element. So our goal in the cache level optimization is going to be simple. We're going to try to exploit these 2 principles, the temporal and spatial locality, to minimize data access times. Now, if you're working with 1D arrays, you're probably going to write pretty good code without even trying. So one-dimensional arrays are stored as blocks of contiguous data in memory. So if we look at a small snippet here of C or C++ code, we're allocating an array of 100 integers. The way this is going to be laid out in memory, assuming these are 4-byte integers, is we're going to start with an offset of 0. We don't know exactly where in memory it's going to be, but we do know that this is going to be allocated contiguously. So element 0 is going to have an offset of 0 bytes. Element 1 is going to have an offset of 4 bytes. Element 2, 8 bytes. 3, 12 bytes, and so on and so on. So if we're trying to write good code here, working with 1D arrays, it's pretty simple. just access those elements in order. So in the snippet that I have at the bottom of this slide, we just show on the process of incrementing each array element by 100. All right, so what's going on with regards to cache? So as I'm executing this loop, we're going to assume, again, 64-byte cache lines and 4-byte integers. We're going to load elements 0 through 15 into cache. So that's 16 4-byte elements filling up that cache line. And then we're going to increment element 0, element 1, element 2 through element 15. Then when we're done, the processor is going to be looking for element 16. It's not available. So now we're going to load elements 16 through 31 into cache. And we're going to increment elements 16 through 31. Now, in reality, the processor is going to recognize the pattern of data access, and it's going to prefetch the next cache line before it's needed. So a question that usually comes up at this point in the talk is, do I have control over cache? So can I be really clever and say, I want to load this particular chunk of data into cache? And there are no programming constructs that I'm aware of that give you direct control over cache. Modern processors, though, directly implement advanced cache replacement strategies, branch prediction, and prefetch mechanisms. So I'm going to say the best you can do is to follow the standard practices of exploiting temporal and spatial locality. And in some instances, you might want to choose optimal parameters based on the cache sizes. So it's going to check. Okay, no questions in the chat. Good. Whoop. All right, here's where things get a little complicated. And that's when we start working with multi-dimensional arrays. Actually, I do see a question. Compilers do have prefetch functions. So Igor, do you just want to chime in and comment on that?
Yeah, so most compilers have the prefetch. I think it's pretty standard by now. You usually don't need it unless you are jumping around the memory randomly, and you can compute what the next access will be well ahead of time. I was able to split codes by a factor of 10 that way, but it's hard.
Okay.
But yes, there are options when you can say, look, I know I will use this this address 10 steps down the line, load it now, if you can do that. But yeah, it's only advantageous if you can do it at least 10, possibly 100 of steps ahead of the time when you use it.
Okay, great. Thank you. Thank you. And I would consider that to be a rather advanced optimization. All right, let's see if there's any more comments. All right, so once we get to multi-dimensional arrays, this is where things get a little more complicated. So from the computer's point of view, there is no such thing as a two-dimensional array. This is what we call syntactic sugar. It's provided as a convenience of the programmer. So under the hood, the array is stored as a linear block of data. And here's where things get just a little ugly. Just like the entire world hasn't been able to agree on which side of the street to drive on. So in the US, most of Europe, we drive on the right side. In the UK and Commonwealth countries, they drive on the left, and that's pretty much locked in. I don't think we're going to consider we're going to convince the UK and Australia and India to start driving on the right, and they won't do the same with us. We have the same issue with programming languages. So there are two conventions. There's what we call column major order and row major order. So in column major order, the first or leftmost index varies the fastest. This is what's done in Fortran, R, and MATLAB. So if we have this small array here of 9 elements, labeled 1 through 9, the way that they're going to be stored in memory is 147, 258, 369, going down the columns. Row major order is what's used in Python, Mathematica, C, C++, and C-like languages. Here, the last or rightmost index varies fastest. So for this same array, the ordering is going to be going across each row, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what this means is that when we want to write optimal code working with multiple dimensional arrays, it's really, really important that we're accessing elements in the correct order. So a properly written Fortran code, if we wanted to add two arrays element by element, is we loop over j, we loop over I, zij equals xij plus yij. Properly written C code, we're going to do the opposite. Here we're going to have the loop over I on the outside, the loop over j on the inside. And here zij equals xij plus yij. Right, so I encourage everybody to go to the examples that I have in GitHub that I posted earlier. And if we were doing this as a summer institute, we would actually do a hands-on. I'm just going to run through the results though. So we're going to compile C and Fortran codes using the Intel and the AMD compilers. We're mainly concerned here with the compiler flags that control the overall optimization. So when we compile code, we can either specify no optimization, -0, 1, 2, and 3. And these are pretty much standard across all compilers. 0 means no optimization, 1 is limited, 2 is moderate. So pretty much any change that we could do that would not potentially affect the floating point results. And 3 is where we're doing aggressive optimization. And we want to make sure, if we're doing this on expanse, that we target the architecture. So if we're using the AMD AOCC compilers, we need to specify the architecture is ZN-ver2. So this is for the Zen 2 core, AMD cores. Intel, we need to specify core equals AVX2. Now, the reason I bring this up is I want to talk a little bit about what the compilers can and cannot do for you. So is data access order really that important? So I looked at some timings for adding together two matrices of size 30,000 by 30,000 using Fortran code with loops nested in the proper and improper orders. So basically going back here, taking that block of Fortran code, looking at the performance with the proper nesting and with the nesting swapped. Now notice that if I swap the order of the nesting, if I have do I equals 1 on the outside, now I'm going to be going through that array with a very large stride. In this case, it's stride 30,000. And we see some very different behavior on the when we use the AOCC, the AMD compilers and the Intel compilers. So we'll start with the AOCC. Here, we'll notice that when we used default optimization and the proper loop nesting, that the code was a lot faster, almost 3 times faster. When we did -0, proper loop nesting was still faster. And as we go to higher optimization levels, we'll see that the code continues to improve. Going from 02 to 03 really doesn't help because there's not much that the compiler can do with this chunk of code. But you'll see that there's always a significant difference, typically a factor of 3 or more between using the proper and the improper loop nesting. So we see improper loop nesting is always slower than proper loop nesting at all optimization levels. So question here from Joe Helmers, how about gfortran regarding so actually, Joe, let me get to that, and then Sugnik, I'll talk very quickly then about the downside of going -03 all the time. Oh, and Igor was asking how big of an n we're using. That this was n equals 30,000. So it was a 30,000 by 30,000 matrix. Okay, so now we're going to go to the Intel compiler. And here was really interesting. We'll see that the default optimization is the same as, appears to be the same as -02. And also in this case, the Intel compiler was smart enough to recognize that I had those loops improperly nested, and it actually rewrote the code to reorder the nesting and get better performance. So, getting back to Joe's question. So I haven't tried G4tran, but that would be a good experiment. I'm not sure if G4tran will recognize the improperly written code and re-nest the loops. The downside of going O3 all the time, right? So there's a comment in here that that it can break some packages. The other thing about O3 is it does what we call more aggressive optimization. So if you're familiar with floating point arithmetic, you need to keep in mind that the algebraic identities that you learned for math when you're growing up in school, say A plus B in parentheses times C, we know algebraically that's equivalent to A times C plus B times C. But when we do floating point arithmetic with a finite precision for the mathematics, we can get very, very small round-off errors. Now, if you compile your code with -03, often it will be faster. You might get very, very, very small differences. You need to judge whether or not those differences are significant. I've actually worked in codes, though, where going from -02 to -03 gave a completely different result, but that was a extremely badly written code where there was, I'm going to say, a highly unstable numerical method. Okay, yep, and Igor mentioned the same thing. Usually buggy code, and that's what we ran into in that application. So Igor, I think if we do 30,000 by 30,000, that we're doing the math, but that's not going to fit into L3 cache. And a question from Kenneth. I thought O2 and O3 didn't change semantics order of operations. Going from -02 to O3 actually could rearrange floating point operations, taking advantage of algebraic identities that may not necessarily be floating point identities. So with that, let me move on. Okay, so a few lessons. Making optimal use of cache is particularly important in memory-bound codes. Sometimes the compiler will help you. In this case, Intel. Sometimes it won't. And I'd really like to see what happens with the I think it was the GCC Fortran compiler. Okay, so one more thing in the chat. Okay, I think we're up to speed now. Okay. So we're getting a little short on time. I'm going to go through these pretty quickly, talk about some of the other optimizations that you can do in your code. A lot of what we call loop level optimizations. One of them is loop fusion. This is one of the most basic loop level optimizations. And this is where we take two loops and we fuse them together. So for example, if we have two loops with the same range of iterations, we combine them into a single loop. Fusing simple loops gives the compiler more opportunities to rearrange instructions and get better performance. And it's even more beneficial if the fused loops use the same data streams, since it allows for better data reuse. So in this case, when I fuse these two loops, both loops we're accessing elements of arrays A, X, and Y. Here, this is going to be considerably faster because when we do the operation calculating Z of I, we already have X sub I, Y sub I, and A sub I not only in cache, they're going to be in register, and they're going to be immediately available for use in the next calculation. Just showing here an example again for the AOCC compiler and Intel compiler, that we do get some definite benefits from fusing these loops. Here it's kind of modest. Assuming that we're using the -02 or 03 optimization, but still noticeable. It's about a 30% boost. Okay, loop fission. I'm going to go through these pretty quickly. You could think of this as the opposite of loop fusion. Sometimes if the loop body is too complex or contains too many data streams, splitting can improve performance. Sometimes it's difficult to decide if loops should be fused or split. If in doubt, you can always try both versions if this is if this occurs in a really computationally demanding function, and see which is faster. One of my favorite optimizations is something called loop invariant code motion. And this is where you take a calculation that outside of a loop, basically that doesn't rely on the iteration, pre-calculate it, and use that result in its place. So again, if it's simple enough, some compilers can do this for you, but we'd recommend doing this yourself. I don't see any downsides in this potentially very big savings. So in this case, again, this is a little contrived, but we're looping over elements of an array, setting z of I equals x of I plus square root of c. There's no reason that we need to do that square root calculation for every iteration. We can do that once. We can pull that out, calculate it before the loop, and then use that result over and over. We can also do this for, there are more complex examples of this. So this is adapted from a code that I worked on a few years ago for constructing animal home ranges from GPS tracking data, modified it a little bit for this example. So we had triply nested loops. Sometimes the invariants are going to be a little less obvious and may even be vectors results. For example, here, we notice that x2, y2 does not depend on the index k. So on that innermost loop, this is a calculation that we don't need to do over and over. Square root of b times x2, y2 obviously also does not depend on the index k. So what we could do is we could take calculations that don't need to be done in those innermost loops, move them outside. So for example, here I took the calculation of x squared, I moved it to the outermost loop. I took the x squared plus y squared and the square root of x2, y2 calculation, move that outside of the innermost loop. And now I use that result repeatedly within the innermost loop. And we can go even a little bit further. We notice that Z2 does not depend on the indices I or j. And of course, calculating the exponent of minus a times Z2 also does not depend on indices I and j. So we could take an entire vector of these invariants, calculate them outside, and now in the innermost loop, instead of doing that expensive exponential evaluation, we can instead just access the element of the vector. And this resulted in a really, really big speed up of this code. Let me take a look at the chat. Okay, what is your thought on reusing an increment variable? Say multiple times in a subroutine instead of ijk. So I'm not quite sure I understand the question. Are you referring to maybe taking your multi-dimensional loop and then flattening it out into 1D? And while you work on an answer, I'm just going to move on because we're getting... Okay, and then question here from Joe. In the loop invariant code motion, is this increasing the memory requirement? Yeah, in a sense it is. If we go all the way back here, we do need a variable to store square root of C. And if we go to the example I just showed, we did have to allocate space to hold that vector. But keep in mind, though, if we're working with three-dimensional arrays in this case, the space that we need for that vector is it's really minuscule compared to the size of our data structure. So here, I'm going to call this a time-space trade-off, that we were able to use a little more memory, but to save a lot of computation time. Oh, so segment, let me get back to your question later. I just want to get through a little bit more material, and we can follow up on that. Okay. All right. Now, another common technique is something called loop peeling. This is where we take one or more iterations and we pull them outside of the loop. I've used this a few times. It's you can often speed up key kernels by doing this. So if we look on the block of code here on the left, where we're iterating over the elements of Z, but you'll notice that very first iteration is a little different. Here, again, contrived example. We're calculating Z of I equals X of I divided by Y of I only if I equals 0. Otherwise, we're going to sum the elements. Again, these are very, very simple examples. Sometimes the compiler will be able to do this for you. Sometimes it won't. Having that logical test in there will, I'll say it's going to break the performance of the loop. You're not going to be able to take full advantage of, say, the vector instructions available in modern processors. But by taking that out, treating it separately, we can often get a big speed up. And here I actually showed this combined with loop fusion. Okay, and one more loop level technique I'm going to talk about is something called loop unrolling. This is where the loop body is replicated and the stride is modified accordingly. And this can help the processor make better use of the arithmetical functional units. So we often hear that that processors could do 8 or 16 or 32 floating point operations per core, per clock cycle. But what we often neglect is that it typically takes 4 clock cycles to get that first result. If we don't have enough floating point operations for the compiler to work with, we often get bubbles in those pipelines. So loop unrolling, where we take the loop body, we replicate it, and then we change the stride of that loop, can give the compiler additional opportunities for optimization. This was a particularly simple example, and I should also say that this is an optimization that the compiler generally does very well. Also, when you manually unroll your loop, it's going to make your code ugly and difficult to maintain. One thing that I didn't show here was if the loop had a iteration count that wasn't divisible by 4, that I would have had to have a cleanup loop at the end, or some cleanup code at the end, to pick up the rest of those iterations. Now, the reason I brought this up, though, is that in rare cases, you might be able to beat the compiler. In years of doing this, this was the only time when I actually did better than the compiler. And this was because the loop body, and here I simplified it. It was actually pages of statements within the loop body. This was automatically generated code for a molecular dynamics application. I didn't do this manually. I wrote essentially a Python script to rewrite the code. And I was able to do for this loop, by unrolling by 4x, I believe I was able to get about a 25% speed up, but something you're not going to get very often. And let me just look at the chat. Yes, and Igor wrote, you know, in my experience, trivial loop unrolling as shown here is not effective. Yes, I agree. But if you have complex logic in the loop to make good use of memory localities, so Igor, I would love to see that. That was the only time when I was actually able to get better performance, but I would love to see a example where you did where you did a loop unrolling and got a speed up. Okay, so we're almost out of time, and I think I'm just gonna finish with one last lesson, and that's what I'm gonna call optimizing for the common case. This was an application I had worked on years ago, collaboration with NCAR, on a code called MPAS, Model for Prediction Across Scales. This is a global atmospheric ocean code. It's based on an unstructured grid, which is overwhelmingly hexagons of different sizes, plus a small number of pentagons and heptagons. It's actually impossible to completely cover a sphere with hexagons. And we noticed within this code, and I won't go into the details too much, but they treated each cell going into it like they weren't sure how many neighbors it would have. So what I did was I optimized the code. I basically rewrote a block of code for the special case where the cell is a hexagon, which was true in about 99.99% of the times, and then created alternative code for looping over cells which are not hexagons. And here we're able to get a more optimal chunk of code, again, in this really key kernel, led to, I think, about a 25%, 30% speed up of this kernel and overall impact on the entire application. So with that, I am going to wrap up. We are at the top of the hour. There's a lot more in here, even in the shorter version of the presentation. We talk about force reductions, where you replace more expensive operations with equivalent, less expensive ones. Interprocedural optimization, where you take a higher level view of the code, see if there are results that are calculated that could be used across multiple function calls, and so on. And with that, I am just going to stop here with my summary slide. Oh. And happy to take any more questions. So yes, Igor, I see the comment there. Your codes must be memory bound. You know, in that case, I was not sure if it was memory bound or not. But yes, some of these are, and I know that your philosophy is that well-written codes should be compute bound, but sometimes you work with what you have. And from Salah, are there any resources that are good for just plain practice problems regarding these loop optimizations? You know, not that I'm aware of. I have a few examples in my GitHub repos, but yeah, we could definitely use some more. And thank you, Joe. So with that, I'm going to stop sharing, and I'm happy to take any questions. I know that was a lot of stuff, even with the abbreviated version, and thank you for sticking with me. Oh, and I see a question here from Siddharth. I'm having memory leak while training neural networks on GPU, but not on CPU. Are there any tools to debug optimized GPU memory? I really don't do much GPU programming. I know NVIDIA has some tools. That might be something you could possibly do with Insight. Oh, and I see Igor weighed in already with CUDA memcheck. Great, thank you. And do we have any more questions? I know we're just past the hour. A few people are beginning to drop off.
All right, if there's no other further questions for Bob, again, thank you, Bob, for giving this presentation. Folks, recordings will be available as soon as possible. I will send those emails, and have a great rest of the weekend coming up. Thanks again, Bob. Take care, everybody.
Great. Thank you, everybody.